Okay, hello everyone. I'm Zibin. In this video, I'm going to introduce and explain the spectral theorem with real metrics. This is closely related to our first three lectures of this semester, which is about linear operator and metric space. Note that in this video, I only focus on the real metrics. I know there is a more complicated version of this spectral theorem that applies to complex metrics, but I think at the current stage, only knowing the real version of this spectral theorem is good enough for economic study and research. Okay, this video mainly contains four parts. First, I will give a brief introduction of the spectral theorem. Then we'll go through the geometric intuition and some intuitive proof. This got to be very interesting. And after that, I will interpret the spectrum theorem in the view of change of basis. Finally, I will go through an application of the spectral theorem in dimensional reduction. I will introduce a technique called principal component analysis, or we say PCA in short. Now let's go into the first part. Okay, the spectral theorem is actually very straightforward. It says that if A is a real and symmetric matrix, in math language, if A transpose equals A, then we have these two beautiful conclusions. First, all eigenvalues of A are real. Second, there exists an orthonormal basis of A consisting of eigenvectors of A, and we can decompose A in this. A equals Q times D times Q transpose. We can write out the matrix form like this. If A is n by n, then Q is also an n by n matrix, where each column of Q is an eigenvector of A. This D is a diagonal matrix with eigenvalues of A on the diagonals. And the third part is just the transpose of this matrix Q. Note that in this expression, I can switch the order of the eigenvectors as long as I also switch the order of their eigenvalues. For example, if I change the order of V1 and V2, then I should also change the order of lambda 1 and lambda 2. So the orders here in this expression is not very important, as long as we are consistent in these three metrics. Here I have two things to emphasize. First, in order to have these two beautiful conclusions, we need to make sure A is a real and symmetric matrix. One counterexample is that for some square matrix A is also diagonalizable, but we do not have these conclusions if it is not real or symmetric. Second, the orthonormal here just means that each eigenvalues of A is orthogonal to other eigenvalues, and all of their length is standardized to 1. Now let me go through the geometric explanation and proof. I know there are many technical and very rigorous ways to prove the spectral theorem, but I think they're not very important. Okay, they're important, but they are not very intuitive. So I'm doing things in a more intuitive way. To understand this geometric explanation, we first need to understand matrix as a linear transformation. So now let's start from something really basic. Say a vector x in R2. If I denote the standard base vector in R2 as vector I and vector j, this vector x can be represented like this. It's just x1 unit of vector I plus x2 unit of vector j. Now, consider a matrix A, 2 by 2 matrix A like this. When we apply this matrix A to vector x, which means we multiply A to the left of this vector x, it gives us x1 unit of vector AC and x2 unit of vector BD. So we can easily plot this linear transformation A times vector x in this way. It means x1 unit of vector AC plus x2 unit of vector BD. So here we kind of have an intuition or a feeling that a matrix is actually a linear transformation of the space. And this linear transformation can be fully captured by the transformation of the base vectors. I will give you more visualization examples about this statement. Now I add some black dashed lines at the background to give you a feeling of this R2 space. Now I'm going to apply this matrix A to this R2 space. What I did first is that I used this blue arrow to indicate the standard base vector I and use this green arrow to indicate the standard base vector J. the first thing I do is I stretch this vector I to the length of vector AC, like this. So its length is now the square root A squared plus C squared. And I did the same thing to this vector J. I stretch it to the length of vector BD. After doing this, I do some rotations according to the angle determined by these A and C, like this. Then I rotate the second vector like this. Now we get this vector AC here and vector BD here. So as you may notice that when I apply this linear transformation to these base vectors, the black dashed line in the background also changes or rotates. So that's how this linear transformation, or we say linear operator A, affects this whole R2 space. The key takeaway here is that a matrix can always be seen as a linear operator, and it transforms the space. And this transformation can be fully captured by the base vector of the corresponding space. Okay, the step two is to understand eigenvalues and eigenvectors. I remember when I first learned linear algebras, these two concepts are the most weird to me because I don't know their intuitions. What I know is just calculation. I think this is not the correct way to learn these two concepts. We have to know their intuitions. Here again, I use this plot to denote the linear transformation A. We do not need to know the exact form of matrix A, but we know it transforms the space like this. As you may notice, for most vectors in this R2 space, it rotates under this linear transformation A. However, please pay attention to these two directions. You can see that these two directions always lies on the intersection of the black dashed lines at the background. So if I plot two vectors on these directions like this, I plot these two orange vectors on these directions, you can see they never rotate under this linear transformation. They only stretch or squished under this matrix effect of this matrix A. So in other words, we can say that for vectors on this blue dashed line, they stay in their own span after the linear transformation. The effect of this matrix A is just to stretch or squish them. They never rotate. Now we recall the definition of eigenvalue and eigenvectors. It says that when apply this linear operator A to the vector V, it is the equivalent as I multiply a scalar to this vector V. This vector V is just eigenvectors of matrix A, and this lambda is just eigenvalues. So in a word, eigenvector is just the direction that stays on its own span under a linear transformation, and the eigenvalues measures how much the vector's own corresponding direction is stretched or squished. Finally, we get back to the spectral theorem. It is very important, so I copy the theorem here. It says that if A transpose equals to A and all elements in A are real, then we have these very nice properties. Here, I give you an example in R2. For example, if I have this matrix A like this, obviously it is symmetric. I can write down the characteristic equations and calculate its eigenvalues lambda 1 and lambda 2 like this. They look like monsters. And if I plug these two monsters into the expression of the eigenvectors and do dot product, which means v1 dot v2, I can prove that v1 is orthogonal to v2. However, this is, in my view, this is not an elegant way to know this theorem, so I will try to give you a geometric explanation in R2. Here I just copied this lambda 1, lambda 2, and v1 and v2 from the last page here. And on the right side, I plot the linear transformation of matrix A. Always remember that I still use the idea of linear transformation to represent a matrix. Suppose this vector AC and vector CB is the base vector after the linear transformation. And then please pay attention to this triangle. I can rotate this triangle here. Note that I'm just rotating the length of this vector. We cannot rotate a vector because that will change their direction and that is not allowed. So this is only the length of this. And I connect these 2 points. I can construct a rectangle like this because of rotation. So this point has height A, and this point, the green endpoint, has height B. So this segment is just the difference between A and B. Also because of the rotation, and we set this matrix like this. So this segment and this segment, they both have length C. Then in this triangle, by the Pythagoras theorem, we can calculate the length of this orange segment as this expression. You may immediately notice that this expression also appears in our eigenvalues. Okay, because this angle is 90 degrees, so we can construct a circle like this. And this orange segment is just the diameter of this circle. So this circle has radius 1/2 of this expression. Knowing this, I will calculate the height of this 4 points. Let's start with this point with height A here. Why this point has height A? Because it has the same height as this point. This point has height A, so this point also has height A. Then we focus on the center of the circle. Why it has this height? Because it is the middle point of the orange segment, and one end point of this segment has height A. The other end of the segment has height B. So this point, it has height, the average of the A and B. This is just high school geometrics. And for this point on the top, why it has height lambda? Because we can calculate the height by adding the height of the center and the radius. That is, this expression adds this expression, and we get exactly the same expression as lambda 1. Similarly, for this bottom point, we can use the height of the center point to minus the radius, which is this expression minus this expression, and we have the exactly same expression lambda 2 here. And then I draw these two vectors, and I claim this red vector is just this V1. This purple vector is just this vector V2. Why is the case? So for this V1, we first go right for C unit, and we go up for lambda 1 minus A unit. So this red vector is just equivalent to this vector V1. Similarly, for this purple vector, we first go left for C unit, that's minus C. Then we go up for A minus lambda 2 units. Okay, and this is just this vector V2. And you can see, because this circle we constructed is symmetric about the y-axis, so this angle is always 90 degrees, according to the middle school geometrics. And if we change the value of A and B, actually these points, this intersect of two vectors, moves along this circle. But no matter where it moves, this angle is always 90 degrees, because this part is the diameter of the circle and is overlapped with the y-axis. So it is the symmetric property that guarantees these orthogonal properties. And in matrix notation, this means that the element here and element here, they should be the same. As long as these two elements are the same, we can guarantee these properties. And so these two vectors, so-called eigenvectors, they are orthogonal. This means that A must be a symmetric matrix to have these properties. And here we kind of use a very simple high school geometrics to prove the spectral theorems in R2. And I think once you draw this diagram by yourself, you can easily understand this theorem. And at least for me, this is better than the text statement. Okay, in the next part, I will interpret this spectral theorem from the view of change of basis of matrix. Here I copy the theorem again. The trick is that if Q is orthonormal, we have the conclusion that the transpose of Q equals the inverse of Q. Why is the case? Because orthonormal means that each eigenvector is orthogonal to other eigenvectors, and all eigenvectors has length 1. If we calculate Q transpose Q, we extend the matrix notation, then on the diagonals, we have VI transpose times VI, which is just the definition of the norm. So we have 1 on the diagonals. And off diagonals, they are all 0. Why? Because these vectors, they are orthogonal. For example, this 0 here is given by the transpose of vector v2 times vector v1. And that is because they are orthogonal, so it is 0. And here, this matrix is just the identity matrix. Because Q is invertible, so we can kind of move the Q to the right side, and it gives us this expression. Q transpose equals to the inverse of Q. And thanks to these, we can rewrite this spectral theorem in this way. The front part is the same. The only difference is this. We can decompose A in this way. Q times D times the inverse of Q. This is associated with our change of basis techniques. Here I also copy the vector and I read out this decomposition in matrix form. You will immediately notice that Q is actually the transition matrix from eigenbasis to standard basis. Here we still consider a matrix as a linear transformation as I explained earlier. And this Q to the power of -1 is just the inverse transpose of this matrix Q, which is the transition matrix from standard basis to eigenbasis. Why this is important? Because if I want to apply a linear operator A to an arbitrary vector x, and I denote the result as vector y, I have two ways to do this operation. First, I can directly apply this matrix A to x and get y. Second, I can first transform x into the eigenbasis, and I apply this matrix D to the transformed x vector. Finally, I transform the result back to the standard basis. Here, the root in the top is completed in standard basis, but the root here at the bottom is completed in eigenbasis. The Q and inverse Q here is just the transform matrix between these two bases. Now let me give you some visualizations in R2. Suppose we have a unit circle in R2, and we want to apply this linear operator A to this circle. From the top root, we can directly apply this A matrix, just as I did earlier to one vector. We first stretch it, then rotate it. Or we can, alternatively, we can use this change of basis technique. We first transform this unit circle into eigenbasis. Here I use the blue dashed line to indicate the direction of eigenvectors, and I apply this matrix D. Recall this D is just a diagonal matrix, so what it did is to stretch or squish the circle along its eigenbasis. And I put these two animations together. You can see these two transformations are exactly the same. Here is another computational example, and I think it is really important, is that if A transpose equals A, that means this A satisfies the condition for the spectral theorem, then how to calculate A to the power of 100. Okay, you can say I put this into some computer software and I can get a result in 3 seconds, but a more clever way to do it is to use this spectral theorem and decompose A into this form. When we extend this form, we will find that the expressions in the red rectangle, their product, it gives identity matrix. Finally, it only left us Q times D to the power of 100 and times the inverse of Q. I write out the matrix notation like this. So the matrix D to the power of 100 is just raising each diagonal elements in D to the power of 100, and we add these transition matrix at the front and back. You can see this is just stretch or like squish the circle in this eigenbasis. It's very intuitive, I think. And this trick I played here is very important in finance because in some classic finance models, we model the transition probability of stock price in this symmetric form. And because of this trick, we can calculate the distribution of the stock price after, say, 100 period by this spectral theorem. And that's like a discrete time Markov chain. Okay, the last part, I will give an application about the spectral theorem in dimensional reduction. It's called principal component analysis. So what is PCA? PCA is a dimensional reduction technique that is very useful in macro and econometrics. Suppose we have n observations and I denote each observation I as yi, and there are p variables xi1 to xip. So I have p variables, but for some reasons, I want to reduce its dimension to d. Here, I use d principal components to capture the variations in these variables. It is possible when we use the spectral theorem. The trick here is that we apply the spectral theorem to the correlation matrix of these p variables. Because of the nature of the correlation matrix, it is diagonal. No, it's symmetric. So we can safely use the spectral theorem. Here, when we write these metrics, these eigenvalues, when we write it in decreasing orders, we can pick first the eigenvectors as the direction of the principal of these principal components. Thanks to the spectral theorem, we have the property that each principal component is orthogonal to other principal components. And furtherly, we have these two additional properties. So PC1 explains most variations in data, and PC2 explains most variations after excluding the effect of PC1, and so on and so forth. Let me give you a visualization in R2. Suppose we have n observations, and each observation has two variables, xi1 and xi2. Here, we use the spectral theorem to decompose it. We find the direction of PC1 that explains most variations in this data, which means that if we project this data onto this PC1 direction, it has the largest variations along all directions. And because of PC2 needs to be orthogonal to PC1, and this is only an R2 space, so PC2 has to be in this direction. We also project these data onto this PC2 direction. You can see this PC2 direction also explains some variance, but it's much smaller than variance on the PC1 direction. The key takeaway here is that PC1 and PC2, they are actually the linear combinations of x1 and x2. And if I need to do the dimensional reduction, I will only pick PC1 as the most important direction. Here is also a visualization in R3. We can use this Python code to generate a Swiss row data like this. And I also apply the spectral theorem to the correlation matrix of these three variables. If I pick this direction as PC1, then I kind of smash all the data points onto this gray plane, and I make the figure like this. After partialing out the effect of PC1, I can choose PC2 like this and PC3 like this. They are orthogonal, and each of them explains some variations in the original data. Note that here, I only plot this for visualizations. I did not calculate the exact direction of these three PCs. It's just for an intuition. Finally, in a more general case, suppose we have a data of 100 dimensions. That's a really large dimension, and we need to reduce it. Again, we apply the spectral theorem to the correlation matrix to get these p eigenvectors. We can choose d PCs that explains more than 95% of its variance. For example, in this so-called scree plot, the blue line here means the variance explained by each PC, and this green line is the cumulative variance explained by the PCs. So I can choose D such that the cumulative explained variance more than 95%. In this numeric example, I choose the first 21 PCs and explains more than 95% of the variance in the original data. So I successfully reduce this 100 dimensional data into this 21 dimension. And that's a big success. Okay, that's all for this presentation about spectral theorem. Thank you for listening, and comments are welcomed.